Sample of problem 5.1. A. Calculate the kinetic energy of a helium atom moving at a speed of 125 meters per second. How much greater is the magnitude, this is B, how much greater is the magnitude of electrostatic attraction between an electron and a nucleus containing 3 protons versus that between an electron and a nucleus containing 1 proton? Assume the distance between the nucleus and the electron is the same in each case. Okay, so let's start with A. So A is an issue of kinetic energy, right? And the kinetic energy of a moving particle is 1/2 times its mass times its speed squared. Okay, so we have a helium atom. Now, what's the mass of a helium atom? This is actually an issue from chapter 3. The atomic mass of a helium atom is 4.003 AMU. But we need to have the mass in kilograms if we're going to do SI units anyways. And we need to have the speed in meters per second. So AMU doesn't work. So we need a conversion factor. The conversion factor is not given here, but it is the following. 1 AMU is 1.661 times 10 to the minus 27 kilograms. That's the conversion factor. So we can find the mass pretty easily. We would just say this 4.003 AMU. And then convert it to kilograms. Like so, right? AMUs will cancel, and you'll have kilograms. So it's going to be a pretty small mass, right? So 4.003 times 1.661 times 10 to the minus 27. And you get 6.649 times 10 to the minus 27 kilograms. So there's our mass. So now we can plug that in. The velocity is given in meters per second, so no conversion factor needed there. So the kinetic energy would be 1/2 times 6.649 times 10 to the minus 27 kilograms. And then that would be times 125 meters per second, quantity squared, right? So times 0.5 times 125 squared, and you get 5.19 times 10 to the minus 23. What are the units? Kilogram, meter per second, kilogram, meter squared per second squared. But that's a joule. 1 kilogram meter squared per second squared is a joule. So that means this is 5.19 times 10 to the minus 23 joules. Pretty small number, right? One little helium atom doesn't have very much, even if it's moving pretty quickly. All right, so there's your kinetic energy. Just to remind you, as we get into these chapters 5 and 10, there's something called the Mks system, which stands for meters, kilograms, and seconds. And this is very common when we're talking about energy or force. We often want to use the Mks system. So the joule is, because it is a derived unit from kilograms, meters, and seconds, it is an SI unit, but it is also an Mks system, Mks unit. Chemists often use centimeters, grams, and seconds. And this causes some confusion. This is called the CGS system, centimeters, grams, and seconds. We often use these in calculations involving things like molar mass. right? Grams per mole. Or density, for example. In density, we use centimeters cubed for the volume, right? A milliliter is a centimeter cubed. So grams per centimeter cubed, that's a CGS calculation. So it can be confusing at times because when we're talking about energy and force, we generally are pretty stringent about using the MKS system. But when we're dealing with mole mass calculations or density calculations, we often use the CGS system, okay? A little bit of a hodgepodge here is the issue. For those of you that are engineering majors, you'll see it even more so when you have to deal with energy units not using the MKS system, okay? Okay, so let's try part B now. Part B says that we want not to calculate, but how much greater is the magnitude of electrostatic attraction between an electron and a nucleus containing 3 protons versus an electron and a nucleus containing 1 proton. So I'm going to draw a little picture here. I'm going to draw 2 pictures. I'm going to draw a picture of an electron, and it's going to be some distance from a nucleus that has a charge of +3. And then I'm going to draw an electron, and the electron is the same distance, but now the proton has a charge of +1. So the distance is the same. Okay. All right. Same distance, but different charges. Let's come back here. Sorry. Let me make a little more room over here. So energy, electrostatic. I'll call this case 1, comma 1. And that would be equal to Q1, or proportional, sorry. Proportional to Q1 times Q2 over D. Okay. So that would be proportional to the charge of the electron, we'll call that Q1, is -1. Charge of the nucleus is Q2, +3 over D, right? So the electrostatic energy of this case, case 1, is, well, let's make it -3 over D, right? Now let's do the same thing for case 2. Case 2, Q1 is still the same, -1, but Q2 is now +1. So the electrostatic energy here would be proportional to -1 times +1 over D. Okay. So our next step is I'm just going to do a ratio. Okay. So what I'm going to do is I'm going to take the electrostatic energy of case 1, and I'm going to divide it by the electrostatic energy of case 2. So that would be -3 over D divided by -1 over D, right? This is -1. It's proportional to -1 over D. Okay. Look what happens. The D's cancel. The minuses cancel, and you get 3 over 1. So you get 3. In other words, the electrostatic energy for case 1 is equal to 3 times the electrostatic energy for case 2. There's more energy of attraction here by a factor of 3 than there is here, right? So more energy, the holding energy, holding those 2 particles together is much greater here in case 1 than it is in case 2. Okay, 3 times as much energy. All right, often for electrostatic energy, it's not bad to think about magnets. Imagine you have like a little magnet. And so if you have magnets holding each other together, there's an energy of attraction, right? So what we're saying is these two are holding each other more strongly than these two are over here by a factor of 3. Okay? There you go.